Today's topic is thermodynamics. Thermodynamics is about taking work and heat and putting them together, see how they interact with each other. The end goal is that we're going to set the stage for learning about engines. And engines are a way that we can turn heat, which is readily available by just burning stuff, into work, which is what we need to make our lives better. We start out with a review of the first law of thermodynamics. If you recall, the first law of thermodynamics said that the total change in internal energy of the system is equal to the heat flow into or out of the system plus the work done by the system. Heat and work are just names that we have for ways of energy being exchanged between the system and the surroundings. Work is force times a distance, so force has to be applied over a distance. And heat, well, that's energy flow that's due to a change in temperature. The tool that we're going to use to explore thermodynamics is a gas, an ideal gas, that's closed in a container that has a movable piston. Sometimes the piston's locked in place to illustrate a point, but basically it's some gas with a piston holding it in place. And we're going to manipulate this in several different ways to try and understand some of the relationships between work and heat during different processes. For a system like this, the gas might expand. And if the gas expands, well then the force that did that work on the piston must have come from the energy that was stored in the gas, the internal energy stored in the gas. And it forced the piston through some distance that we can call delta T. Well, we know that work is equal to force times delta T. Another thing we know is that pressure, which is how we describe force sort of in gases, is defined as force per unit area. So that means the force exerted here by this pressure is equal to that pressure times the area of the piston. So if you could measure this area here, that's what we're talking about. So substituting for force up in the work equation tells us that work is equal to pressure times area times delta D. Now if you think about this area, imagine this to be a circular piston, and we've moved that area through delta D like this. There's the area through delta D. Well, the area times delta D, that's just the volume that we've moved through here, or the change in volume, really. So that means work is equal to pressure times change in volume. Imagine our ideal gas in a container, and now the piston is fixed. We've like welded it in place so it can't move. The particles are in constant random motion, jiggling around constantly inside that container. Well, let's imagine that the container itself is in thermal equilibrium with the gas. The gas and the container are at the same temperature. So that means there's not going to be any Q involved here. There's no heat. There's no energy flow due to change in temperature. Well, there's no work that can be done either because the piston is locked in place, and since work is equal to pressure times change in volume, and volume can't change, that means there can be any work done either. So in a situation like this, where the piston can't move and there's no heat done, no heat exchange, that means the change in internal energy of this system is zero. It's not going to change at all. What we're interested in doing here is exploring the relationships between several different quantities. One of them is energy flow through heating, or what we call heat. We abbreviate that with Q. In addition to heat, we're also interested in exploring what's going on, how it's related to energy flow through working, or what we have called work. A third quantity that's interesting to us is the total internal energy. Some people call this U. I think I'm going to call this E most of the time in this class. And then the temperature, which of course is T. Now E, we're often going to be interested in delta E, change in energy, because we can't really know the total internal energy. And in temperature, quite often we're interested in delta T as well. We're going to look at these relationships through four types of changes. An isothermal change is the first kind, and this is constant temp. So a change where the temperature doesn't change. In other words, delta T is zero. In addition to isothermal changes, we want to explore also something called isobaric changes. Bar is a word part that means pressure. So this means constant pressure, or in other words, there isn't any change in pressure. A fourth type of change is an isochoric change. Isochoric changes are constant volume changes. Some change happens, but the volume doesn't change. That's isochoric. And then the fourth type of process is called adiabatic. In an adiabatic process, Q is 0. In other words, for some reason, you can't have any heat flow. During those four types of changes, we want to look at the relationship between work, heat, temperature, and internal energy. The first one we're going to look at is isothermal changes, and this is based on the old Boyle's law idea. Boyle's law depends on constant temperature. If the temperature is constant, then that means we're going to have a curve, something like this, when we plot pressure against volume. Iso means same, and therm means heat, but really, in this case, it means temp. So this graph is really a constant temperature curve. If our sample gets moved to a different temperature, we cool it down or heat it up, well, Boyle's law still works. Boyle's law just works in a different place. The curve just shifts down. We could do this in several different spots. Same shape of a curve, just in different locations on the pressure-volume continuum. Each one of these things is called an isotherm. An isotherm is a Boyle's law line. There are many possible ones. This is for one temperature, a second, a third, a fourth. We could draw more if we wanted to. One type of isothermal change is something called an isothermal expansion. An expansion means that volume is increasing. If it's happening on an isotherm, that means like here's my starting point, point 1, here's my ending point, point 2, and I'm increasing my volume by staying on this isothermal line. In other words, the temperature doesn't change throughout this entire process, but the gas is now in a bigger space. Let's take a look at one representative particle in this container and look at what it's doing during this isothermal change. That's the particle that we want to look at. We're going to magnify and look at a large-sized view of that individual particle. Remember, it's in constant random motion. It's moving around. Here's our blown-up view. Here's the particle right there. This is a little segment of the piston. Now, watch the motion here. The reason that the piston moved was it got collided with by that little particle. Not only that particle, but lots of particles, all the ones that we aren't seeing in this magnified view, are just bumping into that wall, and that causes it to gradually move outwards. Watch what happens again. Look at the speed of the particle before and after the collision. As it moves in, it's got more speed than after it rebounds. What's happening is some of the energy that goes into bumping the piston, well, the particle doesn't have that anymore. And so the particle slows down. Well, if all of the particles are doing that, if all the particles that are colliding with the piston are slowing down, that means they have less kinetic energy. So the kinetic energy would have to be going down. But if kinetic energy is going down, then temperature is going down, and this is an isotherm, and that can't happen. So in order for temperature to remain constant, kinetic energy has got to be put back into this system from somewhere. Let's take a look at another representative particle to get an idea of where that's coming from. We're going to zoom in on that particle and look at what happens during the change. That particle, the little red one here, that's the gas particle, is in contact from time to time with these blue particles, which are particles that make up the wall of the container. Look at their motion. The blue particles are moving a lot faster than the red particle because it's hot. It must be hot because energy in the form of heating is going to move into the container and heat up the gas, because those gas particles have to get their kinetic energy back up on average in order for the temperature not to go down. Looking at that particle more closely and watching it collide with one individual particle from the wall of the container, Watch what happens to the relative speeds of the blue and the red particle when they collide. The blue particle rebounds with less speed than it had before, and the red particle rebounds with more speed than it had before. So energy was transferred from the blue particle to the red particle, KE in fact, by that collision. If that happens enough time, well, what happens is you've got Q. That's really conduction heat transfer is what's taking place there. So the energy goes back into the container to make up for the lost energy that was lost by working. An isothermal expansion, you can think about it in this way. Think about it in a physical way as this kind of an expansion. Now, as that expansion took place, we've discussed two things must have happened. One is the piston moved, so there definitely was a loss of energy through working for these particles. But if it's an isotherm, we said, the total amount of energy has to stay the same. The kinetic energy can't drop. So there must have been Q coming in to match the work going out. If more energy came in through heat than went out through work, well, then the temperature would go up. If more work was done than energy coming in through heat, well, then the temperature goes down. And neither one of those can happen because this is an isotherm. Delta T is 0. So what that means is the work that was done is exactly matched by the heat in an isothermal expansion. There's another way that we can think about these processes with this schematic diagram like this. We're going to see a number of these. We have a little pink circle here that represents the system before the change. It has a certain amount of energy. We're going to call that E. This little blue rectangle represents the process. In this case, the process is an isothermal expansion. This represents the system after the change. And after the change, there will be whatever E was before plus a delta E if there is one. Now, here's what happened. We saw that there was a loss in energy from the system during this process through work. But we also saw that there was an input in energy from the surroundings by heat. And we also saw that Q was equal to W in order for this to be an isotherm. Well, if Q equals W, then the same amount of energy went in as went out, and so delta E really is 0. That's what that means. So delta E being 0, the energy before and the energy after, same amount of total internal energy. Well, we can imagine isothermal compression as just the reverse process. Say we're starting here and we're going up to here. We're making a smaller volume, but we're doing it isothermally. So we're following this line, going from a bigger volume to a smaller volume, not letting the temperature change. Physically, this is what that might look like. We're compressing the particles into a smaller space, so the system is definitely gaining energy from the surroundings, because the surroundings are working on the system. As these little particles impinge on the piston, they rebound with more energy because the piston is moving into them, and that means the energy goes up. The total energy goes up. That means the temperature would have to go up unless there was a loss that matched it. And so energy has to go out to the surroundings. And if this is isothermal, Q and W have to match again. So looking at our schematic, E is the energy that the system has before the isothermal compression. This is the isothermal compression we're looking at now. And we have energy going into the system through work because it's being compressed. And we have energy going out of the system through heat in order to keep the temperature constant. And if the temperature really stays constant, then that work that goes in has to match the heat that goes out. So that means the total change in internal energy is nothing again. And so E plus delta E, or after, well, the final is the same as the initial. There is no change in the internal energy.